Welcome to our presentation on optimization of an automobile object to be manufactured by casting for our course Manufacturing Technology 1. The team members are Pratyanshu Raj Singh and Richa Kumari. In this project, we have deeply analyzed the manufacturing of brake subsystem and optimized brake disc with the help of SolidWorks and ANSYS.
As we all know, braking systems are designed to do one thing, that is, to stop the vehicle. This may sound easy, but problem starts when brakes must stop a vehicle from a high speed in a short distance. Comparing to the early days, horse-drawn wagons were used at that time. Also, it will be amazing to know that the very first car to have disc brake was the 1949 Crowley Supersport. Now, moving on to the types of brakes. We have disc brakes and drum brakes. Comparing these two, the disc brake has its own advantage. It is completely self-adjusting and has better stopping power. Looking about overall safety and efficiency, disc brakes wins the race. Now, we have components of disc brakes. The first one is brake pads. They are responsible for exerting friction forces to slow down the rotor. Now we have calipers. They are very similar to a piston with pressurized fluid on one side. It exerts clamping force on the brake disc. Now the last one is the rotor. This is the main component which receives the force applied by the brake pads when the brake pedal is pressed by the driver.
Manufacturing of brakes. It usually consists of the following processes: metal casting, metal cutting, metal forming and shaping, and the last one is fabrication and welding. In most of the vehicles, brake discs are made up of cast iron, which has good anti-wear properties and is cheap too. But in high performance vehicles, these brake discs are not up to their standards because the cast iron brake are massive in weight and reduce the vehicle's performance. Permanent mold casting is done, which usually gives out a good surface finish. The molded metal is poured into a permanent mold cavity. Then cores are inserted into the mold, which forms a ventilation cavity in the disc ring to prevent it from overheating. Then the covered mold is sent to a large press, which applies tons of pressure and heating, which makes it stronger. Once the mold is cooled down, it is submerged in cold water, enabling them to pull out the cores and remove the cover of the mold. After that, disc is mounted on the crucible and a funnel is placed at the center of the disc ring, which is filled with fine silicon powder. Crucible is then loaded into the furnace for 24 hours and is heated until the silicon powder is melted completely. The liquid silicon flows into the pores of the framework of the disc ring and forms a layer of a silicon carbide, making it exceptionally hard. After that, drill machine bores the mounting hole on the disc ring. Then a layer of protective paint is applied to shield the disc ring from oxidation. Finally, with the help of computer-guided robot arm, the disc surface is polished.
Heading towards the optimization of brake disc rotor. On the leftmost side, we have designed a simplest disc rotor and this is analyzed in ANSYS software. Firstly, the four holes that are to be fixed are given fixed support as you can see in D part. Then two pressure forces are applied on opposite faces of the disc pad area in order to give clamping force. Also, a rotational velocity is given to the rotor, whose magnitude is kept as 80 radian per second. After the analysis of total deformation and equivalent stress, we found that a disc without vents has more equivalent stress as compared to the one which has vents in it. Hence, the one with vents is preferred for further analysis. After this, we have done the topology optimization so that the shape and design of the disc rotor could be optimized. The visible material in the video is to be removed for further analysis.
The next we have material optimization. We have used grey cast iron and stainless steel 410 and optimized it. The table on the left shows the properties of both the materials. With the same load, grey cast iron suffered a greater deformation by 42% compared to SS410, making it less fit to use. Conclusion: with the design optimization, we can infer that disk with vents provides more strength and durability. With the topology optimization, we can optimize the weight of the disk by reducing the redundant part and hence decreasing material consumption and manufacturing cost. With the material optimization, we can conclude that stainless steel 410 withstands the load better and proves to be a preferred material for brake disc. Thus, our final optimized model contains all the features which makes our brake stand out from others. Thank you.